I want to thank Teresa and to welcome all of you in attendance this afternoon. It is our pleasure to present today's Water Resource Recovery webinar. The purpose of our webinars is to educate attendees on the application of online process monitoring for wastewater treatment, especially YSI IQ SensorNet. The ultimate objective for monitoring is to tie the measurements into control loops to automate process control. With this objective in mind, we are joined today by our Xylem sister company, Sanitaire. Sanitaire is a provider of integrated biological process control software and hardware systems for automation of wastewater treatment through the OSCART platform. The case study described today brings IQ SensorNet and OSCART together for a very effective solution for wastewater treatment plant automation. The benefits we will show you include greater process stability, reduced energy consumption, and reduced chemical usage. My name is Rob Smith, and with me today is Bulbul Ahmed. The two of us will alternate as presenters. The content I present will include the introductory material that immediately follows this introduction, introducing basic concepts of wastewater treatment in each section, and providing details of the process monitoring system. Bulbul will describe the case study facility, the control system, and present the benefits from automation observed for the project. Don't worry, it will be easy to tell us apart. I'm the one with the Midwestern accent. Wastewater treatment process control has traditionally been based on manual samplings and batch tests like the settling test described here, shown in this picture. Manual control is sometimes facilitated through online measurement of critical control parameters. For example, dissolved oxygen. The next level is tying those online measurements into single variable feedback loops to maintain set points for automated control. For example, a valve operation on an airline based on a DO measurement. The fourth level of control is multivariable intelligent control. For example, calculation of an SRT based on temperature and target effluent ammonia. The case study described today is mostly dedicated to level 3 control, although an example of level 4 control is also described in the SRT section. When it comes to activated sludge process control, there are three main operating parameters. Aeration control, to control the desired environment in the reactor, for example, the dissolved oxygen of 2 mg per liter for nitrification. Sludge wasting control, to control the biomass population, for example, to include certain organisms like nitrifiers for nitrification, or to exclude microorganisms that cause bulking or foaming. Sludge circulation is the third parameter to control the distribution of microorganisms between the aeration tank and the clarifier. And a fourth parameter is to set the chemical feed rate to control the level of soluble phosphorus in treated effluent. Today's discussion will talk about aeration control, sludge wasting control, and chemical feed control.
Automated process control and online monitoring case study was carried out in a full-scale conventional activated sludge plant located in Black River Falls, Wisconsin. Those who are not familiar with the location of Black River Falls, it is located about 200 miles northwest of Milwaukee. This is a 0.86 MGD conventional activated sludge process plant designed to meet effluent BOD and TSS of 30 milligrams per liter and a TP concentration of 1 milligrams per liter. This process includes primary clarification, anaerobic treatment, and 3 parallel aeration basins, followed by a final clarification process. Ferric chloride is added as a metal salt to precipitate dissolved reactive orthophosphate that is not removed biologically. One 60 horsepower and 120 horsepower blowers are dedicated for delivering air to aerobic basins. One 20 horsepower blower is dedicated for delivering air to the sludge holding tank. One 60 horsepower blower serves as a standby blower. Before going to the specific challenges with this plant and why this plant was interested in implementing process control and online monitoring, I would like to briefly mention some process issues that we addressed before implementation of OSCART process control and online monitoring. How we addressed will be discussed later on in this presentation. Process issue 1 was the RAS and WAS valve, which was manual. Process issues 2, the air supply line, which is common to the sludge holding tank and aerobic basins. Process issue 3, blowers are all manually controlled. Black River Falls initially installed a DO monitoring system in order to control blower speed manually. A lot of problems there. Operator was only able to control blower speed during work hours. Unstable DO concentration in aerobic basins. The sludge wasting procedure was also manual and mainly based on time. Many problems with this process. The amount of sludge wasted was unknown. What happens if the valve failed to close? What happens if valve is not closed on time? And there was a limited success in maintaining a desired SRT or MLSS concentration. Their chemical dosing for phosphorus removal was also controlled manually with limited composite samples and limited control. Either they are using more or less chemicals to precipitate phosphorus, or they are using more or less caustic to recover PAs in the basin. They also do not have SCADAs. They didn't have any SCADA system prior to the updates. Consequently, reduced process visibility and real-time monitoring and controls. Unstable DO concentration, solid retention time, MLSS, and chemical usage profiles will be discussed with the OSCART process control results. So OSCART is a process performance optimizer, and in this case study we tested automatic control algorithms against manual control to examine process stability, treatment performance, and chemical and energy savings potentials. We tested following 5 controls: aeration control, chemical dosing control, solid retention time control, operator desired or smart, operator desired mixed liquor suspended solids control.
So also, as Bobo mentioned, they had no monitoring prior to this project, so the monitoring system improvements were as follows. A Varian ammonium nitrate sensor, FDO dissolved oxygen sensor, and a V-solid total suspended solid sensor was installed in one lane of the aeration tanks to monitor the mixed liquor suspended solids. The DO sensor was used for aeration control, as Bobo will describe later. The ammonium sensor will be used in future evaluation of ammonium-based aeration control. Stay tuned, there'll be more on this in later webinars and later articles produced by Xylem. The TSS sensor was used in this study as part of sludge wasting control. I want to make a note here that the automatic controls discussed in this webinar were based on the sensors in 1 out of the 3 aeration tanks. That was okay in this case because of a very even flow split. However, in many cases the flow split between basins is not equal, and so independent of control of each basin would be essential to achieve the most benefit. So in addition, a V-solid total suspended solid sensor was installed in the WAS pit to monitor the suspended solids of the RAS and WAS, and it was also part of the sludge wasting control system together with the basin TSS sensor. A P700 orthophosphate analyzer was installed in the effluent building to monitor the effluent orthophosphate to provide for feedback control of chemical dosing, also described later in this webinar. Although there is a monitoring system controller at each measuring location in this example, an alternative configuration with less hardware and simpler installation would have connected all the measuring locations to a single controller through IQ SensorNet one cable network system, the cable that distributes both power and communications throughout the network. The monitoring system also included an MC2 microcontroller module installed in the main control panel. The MC2, as I said, is a mini controller that has no display, but it has the features of being able to interface directly with the most popular Allen Bradley PLC software via Ethernet IP. And that benefit was taken advantage of very much in this project. Besides the easy integration with PLC equipment via Ethernet IP, digital bus technology allows substantially more information to be transmitted than conventional 4 to 20 milliamp outputs to facilitate continuous, reliable data. For example, the status of the sensor. In this case, the sensor on the right is in maintenance mode. Perhaps the sensor has been removed from the basin and is being cleaned, or is being calibrated, meaning that the main value is not displayed and that the control system should not react. The status of the measurement is another example. It is also transmitted. Valid is good, invalid, bad. This indicates, for example, if the monitoring system has detected a problem with the measurement. For example, fouling of the suspended solid sensor, or if the DO sensor cap might need to be replaced. So besides Ethernet IP, other digital bus technologies available through the IQ SensorNet are Profibus, Modbus, and Modbus TCP IP.
As I mentioned during my last presentation or last slide, we addressed some process issues to implement OSCART process control and monitoring. We modified air piping to provide independent air supply and control to sludge holding tank and aeration basins. We added VFDs to both 60 horsepower and 20 horsepower blower dedicated to supply air to aeration basins. We added manual valve. We replaced manual valve with actuator valve with the option of manual control. Added OSCARProcess control system software and hardware system, which includes SCADA system, PLC, and HMI.
Okay, so now you've seen a description of the facility and also the improvements that were made. Now let's see how it worked. So the aeration system is typically one of the largest consumers in a water resource recovery facility. Therefore, aeration control is one of the most common applications for wastewater treatment automation because of the potential for substantial savings in operating costs. And the use of optical dissolved oxygen measurement technology has revolutionized aeration control for its long-term stability and simple maintenance compared with conventional membrane-covered DO technology. The YSI FDO dissolved oxygen sensor is factory calibrated. Routine user calibration is not required. Matching optics of the measurement and reference channels mean long-term stability of calibration and the subsequent measurements. The sensor cap is angled as shown here to minimize interference from air bubbles, eliminating overestimates and providing a less noisy measurement overall. The only required maintenance is routine cleaning of the face of the sensor with a soft cloth. Optional air cleaning is also available to reduce the manual cleaning effort. There is one consumable, that is a replaceable sensor cap, which YSI warranties for 2 years, although actual total lifetime of the cap may reach 3 years or even longer.
Of many forms of aeration control, blower-driven aeration is the simplest one. In this control system, DO controller compares the real-time basin DO concentration with the DO set point and adjust blower speed to deliver air to maintain stable set point DO concentration in the basin. During the reference period, the operator were monitoring DO concentration and adjusted a blower speed manually to save energy and stabilize DO concentration in the basin. As you can see from the figure on the top, they had limited success establishing stable DO concentration in the basin. The basin DO concentration varied less than 1 to over 6 milligrams per liter. However, with the implementation of OSCART process control system and online monitoring, a stable basin DO concentration of 2 milligrams per liter was maintained. The figure on the bottom is showing the blower operation during the reference period and OSCART aeration control period. During the manual control, blower ran at constant speed and mostly 60 horsepower blower ran, whereas the blower speed was continuously adjusted during the automatic control. 25 horsepower blower kicks in when 60 horsepower blower is unable to maintain DO of 2 milligrams per liter. Overall energy analysis for this automatic control period compared to the manual control period showed an average savings of 10 to 15%. These energy savings can be even higher. For example, when the plant was running at 100% blower speed for the week of 10/23 to 10/28, the energy analysis showed 20% energy savings. In summary, OSCART aeration control provided stable DO concentration in the basin at lower energy cost.
Next, let's take a look at chemical dosing control. Addition of ferric or alum for phosphorus removal from wastewater is very common. The cost of chemical, though, is one of the largest operating expenses besides energy for aeration. So minimizing chemical usage through automatic control is one of the simplest and most effective ways to reduce operating costs. Actually, phosphorus can also be removed by biological means very effectively, although the process is more complicated. In either case, the removal mechanism is conversion of soluble phosphorus to particulate phosphorus, which can then be settled out in the clarifiers and removed with the waste sludge. Therefore, achieving the lowest total P requires first converting as much soluble orthophosphate to particulate phosphorus as possible, and process control of clarifiers and filters to capture TSS very efficiently. So whereas total P is the compliance parameter, orthophosphate is the critical process parameter for P. Unfortunately, a probe-style sensor for ortho-P has yet to be developed. Therefore, process monitoring for P removal requires still a traditional cabinet-style wet chemistry analyzer. However, innovations, even in cabinet analyzers, have greatly increased their utility. For instance, the P700 has a wide measuring range, which makes it suitable for monitoring influent, effluent, mixed liquor, and even dewatering centrate. The lightweight 0.45 micron filter effectively removes all particulates, allowing for the use of very small tubing and minimum sample and reagent consumption. Furthermore, the sample pump is located dry inside the cabinet. Together, Taken together, this allows for a lightweight filtration module that is easily accessible and mounted on a slide rail in the basin, as shown in the picture. User programmable automatic cleaning and calibration to a standard provides a reliable and stable measurement that you can count on. The measurement interval is also programmable and can be as frequent as every 5 minutes using the yellow method.
Effluent total phosphorus from a secondary treatment process contains soluble reactive orthophosphate that can be removed by chemical precipitation followed by physical separation such as clarification process. The YSI orthophosphate analyzer measures the real-time effluent reactive orthophosphate concentration. Orthophosphate controller compares the orthophosphate concentration with the set point and adjusts chemical feeding rate similar to a DO control system to minimize chemical consumptions while maintaining effluent total phosphorus quality. As you can see from the figure, prior to the YSI orthophosphate analyzer installation, the operator were adding excessive chemicals, ferric chloride to precipitate reactive orthophosphate and also caustic to recover pH. And their goal is to achieve effluent total phosphorus concentration less than 1 milligrams per liter. And they used excessive chemicals due to their limited control and limited sampling. As you can see from the figure, this plant was able to reduce ferric chloride usage 95% with the implementation of analyzer and control system, and maintain similar treatment performance, which is total phosphorus concentration less than 1 milligram per liter. With reduced ferric chloride consumption, this plant eliminated the need for supplemental caustic addition to maintain alkalinity. Based on this performance data, we estimated a payback period of less than 4 months for a SASIS control system and analyzer installations. In summary, this plant achieved total phosphate concentration less than 1 milligrams per liter, minimized chemical usage, and reduced significant operational costs.
Okay, the last topic for today's webinar is sludge wasting control. Activated sludge process performance, sludge production, and oxygen requirements are all impacted by sludge wasting. Therefore, sludge wasting control is the single most critical process control parameter. However, automatic control of biomass sludge wasting is seldom used. The amount of biomass wasted is typically regulated manually and infrequently, and often targeting mixed liquor suspended solids concentration rather than the actual sludge retention time. Significant improvements are possible by including automatic control of the biomass wasting or even the mixed liquor suspended solids concentration. Before getting into the automatic control, I want to discuss the many different parameters that are used for sludge wasting control. Operators are often trained on many different parameters, and for example, sludge age, which is the measurement of the biomass in the system over the amount of biomass entering, the suspended solids entering the basin. On the other hand, MCRT is a calculation of the total biomass in the system, including the clarifier, divided by the amount of sludge leaving the system. CRT and SRT also are similarly calculated. And to make a note here, those of you that have been trained on F to M, you need to know that F to M is related to all these parameters through the constants for growth and decay, so that although it's not directly, the F to M is basically inversely proportional to these parameters. In a couple slides, Bobo will discuss SRT, or solids retention time, in more detail. But regardless of what control you use, total suspended solids monitoring is essential. And the YSI V-Solid TSS sensor is an optical reflectance-based probe with two built-in factory calibrations. One for mixed liquor suspended solids and return activated sludge solids, and another for primary sludge or thickened sludge. In either mode, the operator can report the concentrations in milligram per liter or percent solids. It has built-in ultrasonic cleaning system, the UltraClean technology, which greatly slows the accumulation of sludge on the sensor, reducing maintenance requirements. There are no wipers or external mechanical components that need to be replaced, as you can see from the picture.
SRT, or solid retention time, is a design parameter that measures the duration of time in days that microorganisms spend in the system, and calculated as basin biomass divided by wasting rate. We can calculate basin biomass through online measurement of MLSS concentration since basin volume is constant. Similarly, we can also calculate wasting rate through online measurements of TSS concentration and flow rate. SIMS, Solid Inventory Management System. This is an automated sludge wasting controller to maintain a required solid retention time or mixed liquor suspended solids concentration. Of many benefits, it improved overall improvement and consistency in effluent quality, improved stability of the plant operation, improved settling characteristics, reduced energy usage associated with aeration and sludge handling. It also reduced operators' workload and maintained stable operation during weekends and holidays. This graph is showing the impact of sludge age or solid retention time on the biological treatment. At low sludge age, the ammonia removal efficiency in the graph status per unit power is very low. We do not get sufficient treatment, but we can save energy. At high sludge rate, the ammonia removal efficiency per power starts to again go down. We get sufficient treatment, but to an unnecessary high energy cost due to endogenous respiration of the old sludge. There is a window where the ammonia removal efficiency per unit power, input power, is at the peak. We get sufficient treatment at lowest possible power input. This is where we want to be. The mass to waste to stay within this green area depends on several factors, such as influent loads, temperature, ammonia requirement, dissolved oxygen, etc. So they vary over time and between plants. It is very difficult for an operator to manually adjust mass wasted to stay within the wanted green area. Most common is to keep the biomass too high. Want to be on the safe side. Treatment goals are met, but energy is wasted. SIMS control system provides greater operational flexibility. The operator can choose any one of the 4 modes of operation. In time mode, operator can simply choose a specific period of time for each wasting event. In MLSS or SRT mode, operators can select a desired MLSS concentration or SRT respectively. Or operator can choose a smart SRT mode where controller calculates SRT required for complete nitrification based on process parameters. And SIMS is a trouble-free control. SIMS includes a large set of safety nets which ensure a safe and trouble-free control. Independent on operating mode, all control actions are made with careful change to ensure that the process is stable. Fast process changes can otherwise disturb the biology and cause problems such as filaments. These kinds of issues are avoided through the included control stabilization. Since SRT is an important parameter affecting the process health, it is carefully monitored and maintained at a healthy level, even the operator selects to run in MLSS mode. Let's see some results that we observed at this wastewater treatment facility. So the first result is operator desired solid retention time control. Before SIMS control implementation, operators were manually adjusting wasting during work days. From the figure, you can see that the daily SRT varies from 8 to 22 days. Whereas with the SIMS control implementation, the plant was able to maintain operator desired SRT, which was 14 days, and later on it was 12 days. So from figure, you can see it's a stable operation and optimized treatment. Similar to SRT, operators were manually adjusting wasting during work days before SIMS control for MLSS control. As you can see from the figure on the right, the daily MLSS concentration varies from 1900 to 2600 milligrams per liter, and no control during weekends or holidays. With SIMS control, this plant was able to maintain operator desired MLSS concentration of 2100 milligrams per liter. Again, very stable operation with implementation of SIMS control. This plant also tested process optimized SRT controller. Under this control strategy, the desired effluent concentration was set at 1 milligrams per liter. This controller calculates required SRT using process parameters. Based on this calculated required SRT, controller calculates much needed to be wasted. As you can see from the figure, this controller system maintained SRT close to the process optimized SRT. So at this time, I will be summarizing all the results that we observed. The key message here is the process stability. As you can see in all cases, in case of dissolved oxygen, you can see that the standard deviation with the OSCART process control system is 0.05 milligrams per liter. And we showed 10 to 15% energy savings. In case of MLSS and SRT, the controller was pretty tight and is staying at the set point and meeting a treatment goal of TSS, BOD, ammonia less than 1 and TP less than 1. The chemical dosing, they are using almost like 1,000 gallons per month, and with the automatic control, they are using a less than 50 gallons per month. So that gives a significant amount of savings annually, which we calculated approximately $73,481. And I worked with these plant operators on day-to-day basis and maintained this pilot projects, and I included some of their comments. When I talked about the blower-driven aeration control, I got a message from Bill, hey, I like the way the blower is kicking on and off. I do not need to go to the blower room, or I do not need to check back on weekends or holidays. Life is very simple. I got the same message when they were running on SIMS MLSS control, because this is the first time they are wasting automatically. And they were very happy with the performance that they wanted 14 days, SRT is 14 days. They wanted 12 days, the SRT is 12 days. At a high water temperature, they wanted to run smart SRT. This plant is running a smart SRT and providing an effluent, which is the ammonia is less than 1 milligrams per liter. And with the implementation of orthophosphate analyzer and the controls, they're saving significant amount of money which they spend for chemical uses and caustic uses. So overall, this plant operators are pretty happy with this automation and online monitoring. If you have any questions and want to get an operator's view, you can call Bill or Rick, and their phone number is attached. And you will have the presentation slides later on.
Okay, so just to also a reminder that even if you're not quite ready for a full-blown automated wastewater treatment plant, you can get started with just the IQ SensorNet process monitoring system. Maybe just one DO probe, or maybe you want to monitor TSS, and you can build on that system as your confidence grows and as you want to take on more challenging projects. Also, we will take some questions today, but if you're going to WEFTEC and want to see Bulbul and myself or other Xylem experts in person, do attend the sessions shown here in the rooms shown to hear more about success stories. Also, stop by the Xylem booth, number 1041, and you can get a chance to win a YSI multi-lab benchtop instrument, win an IQ SensorNet System 182, or get a 15% off promo code good for any YSI multi-lab, TrueLab, or handheld system. And if you still need more information, there are lots of ways to get it on the internet, through the web, YouTube, SlideShare, or telephone or email. And here is the information you'll need to get to all of those resources. Thanks again for your time. Bulbul and I have enjoyed making this webinar presentation today, and now we'll field some questions.
Okay, so let's start with the first question here. Okay, sorry for the delay. Our first question here is, did the automation of SRT control result in measurable energy savings? Was the key benefit of SRT control process stability? How was process efficiency measured in relation to the implementation SRT controls?
Excellent questions. In this specific project, we showed the process stability with the automatic SRT control, but we did another project where we quantified the energy savings with the implementation of auto SRT, and we see that when their plant was not running with automatic SRT or a smart SRT control, it was using 12% more energy compared to the smart SRT control.
Okay, on to the next question. Can your equipment measure real-time TSS, or is it a correlation with turbidity and lab TSS measurements?
Yes, this is Rob, and I'll take that question. It actually does provide, I mentioned, a factory calibration so that the reflectance measurements, which are at various angles, for example, 60 degrees, are then programmed into the sensor to provide a suspended solids concentration measurement. And so with if there is such a thing as a typical mixed liquor, that should provide a sufficient level of accuracy without having to develop your own correlation. On the other hand, if you need a higher level of accuracy, or you have a unusual, we'll call it mixed liquor, you can program in two types of calibrations. One is a correction factor, or the other is up to an 8-point value pair calibration. So the simple answer is that it is a correlation that's been programmed into the sensor, If you need higher accuracy, then you can perform your own user calibration.
Okay, on to the next question. What type of control was used for dissolved oxygen? PI, PID, MPC, adaptive, etc.
For this project, we have used PID controller to control the DO.
Okay, how was the $73,481 US annual chemical dosing saving calculated?
During the presentation, I showed the chemical uses for a specific time of period when there was no analyzer and control, and a period with analyzer and control, and we calculated the energy savings on that period based on the ferric chloride price and caustic price and their uses, and we projected that to a 12 months savings, which is $73,481.
I know you said the TSS probe had pre-calibrated variables such as MLSS or RAS or WAS, but do you still need to calibrate or input a fudge factor to take into account the possibility of different particle sizes in a specific basin?
Hi, this is Rob again. Yeah, very similar question to the last one, and yeah, so if you've got a mixed liquor and maybe you've got a little some atypical particle sizes or other things, you can actually program in a particle or a correction factor, sorry, to correct for that. So as I said again, if the user calibration is not giving you the numbers, the correction factor can correct for various. Usually the correction factor will correct for things in the environmental conditions. So let me give an example besides particle sizes. In a pipeline, the environment may provide certain interferences that are constant, but don't allow you to get an accurate enough suspended solids measurement. So by programming in that correction factor, you can basically offset that interference and give you the true measurement. I also want to add to this response and the previous one is that the only way there is to measure actually TSS is through a gravimetric procedure in the lab, so involving filters, ovens, and et cetera and so forth. So that is the only suitable reference measurement. All other measurements are really correlating another signal, for example optics, to a suspended solids concentration. Thanks for the question.
Thanks, Rob. Okay, on to our next question. Does the phosphate analyzer need to be located in a building, and what is the approximate cost?
This is Rob again. No, so the phosphate analyzer can be purchased with a optional climate package, which enables it to be installed outdoors. And in fact, that's really the preferred application. Although in this example, we were monitoring the effluent, ideally you would want to monitor closer to where you're actually adding the chemicals. So there was at least the retention time of the clarifier between the time that the chemical was added and the time that the orthophosphate was measured. So definitely this is meant to be on the rail outdoors. And the cost of that is, I'm going to let you contact YSI for pricing information.
Great, thanks Rob. Does the SRT control require continual wasting or can intermittent wasting occur?
This is Bulbul. This wasting event can be continuous or can be intermittent. In this project at Black River Falls, this wasting event was intermittent. So we used intermittent cycles throughout the 24-hour period to waste. Thanks.
Thanks, Bubble. Great questions. How feasible would it be to implement dissolved oxygen control for membrane bioreactors? Will space and location of the sensor be an issue?
This is Rob. I'm going to take that first. Dissolved oxygen control in a smaller reactor, assuming a membrane reactor is a more complete mix, location is probably not a factor. So in a particular zone, so you could locate it anywhere in there. There are other things to be concerned about with a membrane bioreactor. Yeah, a lot of these have air scour, for example, which is not necessarily a process DO, but would occur nonetheless. I will let Bulbul add any specific comments he has on MBR applications.
Now, as a process engineer, I do not have experience on working with MBR, but might be the location of the probe.
Okay, if I were to connect the 2020 XT controller to a PLC such as ABB, I can collect the measurements through Ethernet, or must there be a 4 to 20 milliamp output from the controller?
Yeah, so this is Rob, and so traditionally 4 to 20 milliamp has been, and probably is overwhelmingly, the choice for control signals. But if your PLC is compliant with a particular digital bus technology, then you would be able to go directly, you would be able to transmit that communications information over that protocol to your PLC. Keeping in mind, though, that with Ethernet IP, at least Ethernet IP and IQ SensorNet, it is specially designed to communicate with Allen Bradley, the most popular PLC platform. It is possible to communicate with other platforms, of course, but just overwhelmingly that particular platform is the most popular, and so we put in special features to allow a simplification of implementation of that platform. But Profibus, Modbus, and Modbus TCP IP are also possible. Thanks.
In the first slides, you showed an anaerobic basin. Was this an anaerobic selector, or what was it?
So based on the process flow diagram of this wastewater treatment plant, this is an anaerobic reactor that the effluent from this anaerobic reactor flows to the aeration basins.
Regarding the inline orthophosphate analyzer for chemical dosing control, are there any troubles with the analyzer sampling thicker liquids such as MLSS for ortho-P determination, such as clogging or fouling?
This is Rob. I can field that question. We are, the specs say the sample concentration is up to 6,000 milligram per liter TSS. That should cover most mixed liquor suspended solids applications. And so up to that concentration, there shouldn't be any difficulties with sample volumes or sample deliveries and plugging of the tubing inside the photometer or between the filter and the sample pump.
As a second part of that question, if monitoring OrthoP 24/7 normally, how often would reagents in the analyzer have to be changed or replenished roughly? 1 week, approximately once a month?
Yeah, so there's a trade-off there. As we've said, you can do up to a 5-minute measurement interval, and your reagents will last 4 months at that rate of usage. Obviously, the longer the sampling interval, say 10 minutes, you could expect up to 8 months of reagent. The reagent will last for up to 8 months. So 4 to 8 months is the, I guess, the simple answer to that question. Thank you.
Thank you, Rob and Bulbul. It's been quite humbling to sit amongst PhDs today. We really appreciate you attending this webinar. We hope you found it useful. Please take just a few minutes to complete the brief survey at the end and let us know how we can better serve you. We really appreciate all the great questions today. Unfortunately, we were not able to get through all of them. We will follow up with you directly and get back to you with all your great questions. So thank you.